But we'll recap a little bit of what we did on Friday or Thursday last week, someday, right? It was a day. We did stuff. We'll recap that here briefly, and then we'll pick up where we left off. We're in the midst of talking about matrix multiplication. We still have quite a bit more to talk about in regard to that. And certainly you guys probably need to see more than one example of doing matrix multiplication, which is perfectly reasonable place to be at because it's a little bit tricky and you've seen one example, which is probably not sufficient to feel confident about doing it a bunch of times. So we'll do that and then continue on talking about these last couple of matrix properties and operations, and hopefully we'll wrap up that stuff today and we can start talking about applications next time and circling back to like how in the world are we going to use this to solve systems, which was kind of the goal, right? Everybody sound okay? Cool. Okay. So just to recall here a little bit. So last time we asked you to do things like find the dimension of something. So the dimension for a matrix like this would be what? This is a 3 by 1. So we have 1, 2, 3 rows and 1 column. We always write them in this order where we do rows first and columns second. And when we write a dimension, we write it like we would a dimension of a room with that X in between it. We don't actually multiply 3 and 1 together and call it 3. So I just wanted to clarify. These are things that I saw people doing in homework here and there. So I just want to just clarify a little bit. Is everybody okay with that idea? Okay. Oh, thank you, Janet. That's better, right?
Yeah.
Okay. All right. So we talked about dimension. And we talked about some basic matrix operations like addition, subtraction, and scalar multiplication. So we talked doing something like this, right? Where I've combined all 3 of those operations just into one problem to get the feel for it. Everybody okay here? This looks like something kind of like what we would have done in the homework, right? So first thing that you should do is you should check to make sure that this problem is even possible. So when I add or subtract 2 matrices, what do we have to have true in order to add or subtract them? Have to have the same dimension. So let's first check their dimensions real quick. So what is the dimension of the first matrix? 2 by 3. Yep. And the second matrix? Okay. So we can definitely add or subtract these. Everybody agree with that? Okay. So let's go ahead and do that. I'm going to do it all in one step. So I'm going to do 2 plus 3 times 1 minus 2. That's going to be my first entry. Does everybody see how I did that? I took 2 plus 3 times 1 and then 2 to get my first entry. And I'm just going to do it that way rather than doing it as a bunch of separate steps. Are we okay with just squeezing that all together into one step like that? It just feels like it's going to be, you know, a lot less writing to do that. Okay. Did that look right to everybody? My little checkers out there. Did I type everything or write down everything correctly? I hope so. But you know me. You know I make mistakes. If you see anything, holler at me. Let's see. That's 2 plus 3 minus 2. That's 3. -1 plus 0 minus 3 is -4. 5 minus 9 plus 1 is -3. 3 plus 30 minus 6 is 27. 6 plus 21 minus 7 is 20, right? Yeah. And then 4 minus 27 minus 0 is -23. Everybody's okay with that? Overall, it seemed like we're pretty good with these basic matrix operations, right? Nothing too complicated going on, nothing too tricky, which is good, right? Let's do another matrix multiplication example. Sound good? Okay. So again, before we start in on trying to do one of these problems, we should first check to make sure that it's possible. So to do that, we have to compare the dimensions, right? The dimensions don't have to be equal. What has to be true about the dimensions, though, for matrix multiplication? So the number of columns in the first matrix has to be equal to the number of rows in the second matrix. So the dimension of the first matrix is what's the dimension of this first matrix on the left here? That's a 3 by 3. And the dimension of the second matrix is a 3 by 2. So since the columns of the first matrix are equal to the number of rows in the second matrix, we can do this problem. And it tells us that our answer is going to be a 3 by 2. Is everybody okay with? So it's going to be a little bit like each parent. You remember the falling in love story?
Oh,
yeah. Yeah. Okay. So far, so good? So I'm first learning to do this. I think what's helpful is to go ahead and draw what our answer is going to look like. So our answer is going to be a 3 by 2. Okay with that? So for our entry 1, 1, we're going to take row 1 and multiply it by, I'm sorry, that is the wrong order. We're going to do row 1, I said the right, times column 1, and then we're going to add up those individual entries then. So I'm going to do first together plus the second thing from each multiplied together times or added or plus, jeepers creepers, the third thing in each multiplied together. Is everybody okay with where those numbers come from? Okay. And then I'll do the next spot is using row 1 and column 2. So that's going to be 3 times 2 plus 2 times 0 plus 1 times negative 5. Are we all okay with where those numbers come from? And again, like as you get more comfortable with this process, this will speed up for you. I'm just trying to go pretty slow and give you a lot of notation about where things are coming from because you're just learning how to do this for the first time, right? So if anything, if I want to, I'll err on the side of over-instruct versus under-instruct on this. So if you're doing this in like jeepers creepers, Mr. Kulik, can you just pick up the pace on this? Like I get what you're saying, but I'm going to continue to kind of go quite slowly through this because, well, that's the way I want to go this time through. You know, I just don't want to leave anybody like struggling to kind of keep up on it. So I'm going to do all this silly color coding and all that so that when you go back and you look at your notes, things hopefully make sense and you can see where these numbers come from. Oops, need a color for that one. Okay, so we've got that all worked out now. All we need to do is do our simplifying. So 3 minus 6 minus 4, or plus 4 is 1. And then 6 plus 0 minus 5 is 1. And then 0 minus 15 minus 12 is negative 27. And then 0 plus 0 plus 15 is 15. And then negative 1 minus 18 plus 8 is negative 11. Plus 0 minus, or I'm sorry, negative minus 10 is negative 12. Is this okay? Let's give you one more that you guys can try here on your own, and then we'll go through it as a group. And then we'll move on and start talking about properties of matrix multiplication and finish up our last couple matrix operations that are direct consequences of some of these properties. So just wherever in your notebooks or on a separate little scrap or sheet of paper, you're not turning this in or anything, so just wherever you want to do it. But let's try to do this one here. So we're just going to practice multiplying these two matrices together. So just in your notebooks or wherever, so take your time. We'll take, 5, 6, 7 minutes or whatever kind of needs until we feel like we've had a chance to work on this. I've wrote the answer down. I did this quickly in my head, but I think that's correct. So as you're doing things and you want to check, that's up there to check from. Obviously, if you think I made a mistake, let me know. That happens. I was pretty sure that was correct, but again, I did it quickly in my head, so mistakes happen. But I just did it a second time here in my head, and I think that's pretty sure that's correct. So if there's a mistake, it's awful embarrassing for me. Okay, has everybody had a chance to give this a shot? Anybody still working on finishing things up? Bless you. You're welcome. There's nothing worse than a sneeze into your mask, right? Yeah, it is gross. Anyways, so we feel okay doing this, or at least a bit better. Obviously, you have a homework assignment where you get to practice this, but figured this would be good to at least give you a chance to try it on your own here once. If there's no questions, we'll kind of continue. Okay. All right. So last time we had made the observation that A times B doesn't necessarily equal B times A, right? Because we noticed that we had an example where, like, if A was a 3, we can do A, right? You guys remember that from last time? That was like the last idea we had mentioned before we had to go. But I'd asked you, is there ever going to be a situation which A times B does equal B times A? And I asked you to maybe try to think about that over the weekend and see if you guys... How many of you forgot about it? Me asking you to do this. That's perfectly fine if you did. Honestly, I didn't really expect anybody to come up with anything, but it was, you know, it's an interesting question here that we'll spend some time talking about here for the next little bit. So, what things certainly have through if A times B and B times A are going to be equal? Yes, Sydney. Good. So we'd have, what we're going to say is have to have the dimension of A and the dimension of B both have to be, we'll call it n by n. We call that kind of a matrix a square matrix. Just like a rectangle that's 2 by 2, you would call a square, right? Because the side lengths are the same. So let's just make up a pair of 2 by 2 matrices and see if A times B is going to equal B times A, right? That's the smallest example where this could trivially be, or not be trivially true, right? If we talk about 2 1 by 1 matrices, obviously A times B is going to equal B times A, right? Because if you multiply a 1 by 1 matrix, it's just the same as multiplying like one number by another number, which is commutative. Does that make sense? Okay. So let's look at an example and see if that works. So let's say A is the matrix 3, 5, -2. I'm just picking some random numbers here that aren't too inconvenient. So maybe 0, 6, 3, 1. So let's see, 3, 5 times 0, 3. Well, that's going to be 0 plus 15. And then 3, 5 times 6, -1. That's going to be 18 minus 5, so 13. And then -1, 2 times 0, 3. So that's 0 plus 6, so 6. And then -1, 2 times 6, -1 is -6 plus -2, which is -8. And then let's try to reverse the order and see if we get the same result. So 0, 6, and 3, -1 gives me 0 plus -6, so that's -6. And already we could stop here, right? Because what can we say about these two matrices? Yeah, they're not equal. That's for darn sure right away. Everybody agree with that? So I'm not even going to bother finishing. Okay, so this is maybe surprising, right? You know, what would be natural here to think is like, okay, if I just correct for a situation where, you know, like I can't do the multiplication both ways and get the same size of matrix. If I make it so that, yes, A times B and B times A are both going to be defined, and I'm going to get the same size matrix each time. Even if I fix that part of it, still they're not guaranteed to be commutative. Right? That's what we've just shown. Does everybody see that? Well, I think the natural question at this point is, right? We tried to fix a situation where they definitely would commute, and it didn't work. Well, what do you think the answer to this is? Do you think there is ever a pair of matrices that will? So no. This is a nice idea. Can you tell me specifically, like a pair of 2x2s that you're thinking of?
All the numbers were 2.
And the second. Okay. So this is situation where just like A times A, right? Clearly is going to equal A times A. So yes, there's definitely some situations where this is going to work. Can we find a situation where A and B are different and it still works? Sydney? Okay. Or 6, 4, 6, like that. Well, let's see, right? That's what we do. We think we have an idea. So 4 times 4 is 16, and get that twice. And then 4 times 6 is 24, and we'll get that twice. 6 times 4 is 24, we'll get that twice. And 6 times 6 is 36, so we'll get that twice. And now we'll switch the order and see if that works. Ask every year to this honors class. Nobody's ever suggested this situation, Sydney. So I honestly don't know if it's going to work or not. So that's why we're actually doing it. So we have 4 times 4 is 16, and 6 times 6 is 36. So that's going to be 52. And already we see that we didn't work. Ella. Okay. So let's write it this way. Let's do it a little bit more generally. I'm going to just say A's and then B's. And this will take care of the situation that you've described where like the first one, they're all the same, and the second one, they're all the same. And potentially different, right? We haven't stipulated that A and B can't be equal, but clearly we know it works if they are equal. So if I do that, I get A times B and then A times B. So I have 2A, And then I get 2AB and 2AB and 2AB. So we get 2AB, 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 and 2AB. So yes, we found one general situation. So that's sweet. Very cool. We got one. And that covered a lot of situations, right? Since we did it very generally with just A's and B's. Sydney? Oh, I'm sorry. Were you raising your hand? No. Okay. You're the other Sydney, though, right? Okay. Sorry. I thought you were raising your hand. I think you must have just been messing with your hair or something. My apologies. But I was trying to call on you, and you looked at me like, why are you looking at me? So I was like, oh, okay. I made a mistake. I'm sorry. So that's good. We have one situation. So my next question then becomes, does A times B equal if is not a matrix where all so can we get this to work if either A or B, well, let's say just not, if neither A or B is a matrix with just the same thing over and over and over, right? You know what I mean, guys? You know how like we had here, A was and B was. Can we do that if neither of those two things are true? If all the elements in A aren't equal and all the elements in B are not equal, can we get this to work still? So Ellie, you did a good job on identifying one situation that works. That was good. Can we think past this situation? Can we get this to still commute past there? Sydney. Okay, so Sydney says this is good. So if A is all zeros and B can be whatever, then A times B is going to equal B times A, because both of them are going to equal the zero matrix, right? Again, we're stipulating still that A and B are both square matrices of the same size. They're both n by n's. Like 2 by 2s like we've been working with. If anybody was objecting to that, like, whoa, what if B's not 2 by 2? Like, we've decided that they're talking about 2 by 2s here. So that's good. And again, right, this is not really the 2 by 2 subscript down there to remind us that that's not the number 0 there. That's the zero matrix. That's the letter O. Hard to tell just by looking at it, but we'll put that little subscript down there to give it a dimension so we know that what it is that is, or remind us anyways. So good. That's my issue. That is that still A is a matrix with all one number in it, right? Can we get this where either A or B, none of A or B is just a matrix just with one number in it over and over and over again? Well, yeah, Natalie. No.
You have one matrix where it's 4, 2, and 2, 4.
Okay, 2, 4, 4, 2.
And B would be 4, 2.
Like that is what you're saying, right?
Yeah.
Is this,
Is that what you want? Yes.
this is what you're saying?
Yes.
Let's check. Yeah, no, this is an excellent idea, I think. So row times column, that's 8 plus 8, so 16. Row times column, that's 4 plus 16, so that's 20. Row times column, that's 16 plus 4, that's 20. And then row times column, that's 8 plus 8, that's 16. And we flip it. So 4 times 2 is 16 and 4. That's 8 and 8. Right? Yep. And then, oh no, my apologies. Goodness gracious, Mr. Kulik. You got going too fast. That's 4 and 16. And that one's 8 and 8. So yeah, that worked. So how would we generalize this? If A is equal and B is equal to and as an aside here, B, call that A transpose. And what the transpose operation does is the columns for A, how do I want this? Maybe, no, hold on. Yeah, that's not right. That is not the transpose. Let me erase that. It's irrelevant. I wasn't ever going to ask you anything about transposes again, but here's my next question now. So this worked. That was great. Can we come up with a situation where only A has to look some certain way, but B could be period? Now we've already done this where with matrix, B could be anything. Can we figure out a situation where A, we only have to say something about A, but B can be anything else? Sydney, you have an idea? Well, we're all just guessing here. Like, your guesses are just as good as anyone else's. So you want A to be all 1? Okay, let's try it, right? Because nobody knows, other than me in the room, like if this is going to work or not. And this is an absolutely a reasonable thing to try. So let's try it. I don't know. Just something arbitrary, right? Just pick some random numbers. Is that okay? It'll be harder to see what's going on. But this is a good idea. So I'm going to write this out because this is a good idea. It's not quite there, but we can certainly get there by taking what this idea. Oops. Come on. Okay. So we can see right away that they're not going to be equal, right? But let's look if we just looked at the result, we'd have no clue as to how close they were to being equal or how we could change A to make them equal. What I want to point out, though, is that in each of these, one part of this addition problem is the same. Everybody agree with that? So what we want is the other part of that addition problem to just go away. How could we do that? Sydney? So we're going to use a 0, absolutely. So let's look at this. So this one right here, we want to be a 0, correct? Which one in A did that come from? Mia? Yeah, it would be this element 1, 2 in the first row but second column. All right. Let's look at this number 1 here. We want that number 1 to be a 0. Which one is that? Yeah. It's also 1, 2. Hey, this is looking up. Okay. Let's now look at this one. We won't need that one to be a 0. Which one does that correspond to? 2, 1. Okay. And we also want this number 1 to be a 0. Also corresponds to 2, 1. So what if instead it's 1, 0, 0, 1? Let's try that. Maybe that'll work. What do you guys think? It's going to. And in fact, if you take a look at the result, you should notice something else. What else do we notice? It's what? Yeah, that basically had A times B is equal to B, and B times A is equal to B. That's what we noticed, right? Well, we have a special name when that happens, right? What is this matrix A kind of acting like? What real number is this matrix A acting like? The number 1, right? So that has a name. That's called the multiplicative identity. Okay. The multiplicative identity for matrices is an n by n matrix with ones down the main diagonal and zeros everywhere else. If matrix multiplication is possible, A times B will give us B. And if B is also an n by n matrix, A times B is equal to B times A, which is just B. This is for any n by n matrix. So we're going to give A a special name. We're going to use the capital letter I to represent such a matrix. Why do you suppose we chose the capital letter I? It kind of looks like the number 1, and this matrix acts just like the number 1. So we just did it to help remind us that, oh yeah. So for example, the multiplicative identity for 3 by 3 matrices would look like this. When I say ones down the main diagonal, I'm just talking about the longest diagonal starting in the left-hand corner. And so like the 4 by 4 version would look like this. And you get that. I hope you get the idea from there. Sydney? Yes, must be a square matrix. Yeah, so we even included that in the definition, right? We said it is an n by n matrix. So the identity must be a square matrix. Now, so Natalie asks, what happens if we have this, right? That's what you're asking? Okay, so let's do it for a 2 by 2 because I don't want to do that much multiplication for a 3 by 3. Just see what happens. I could tell you, but it's more fun to just show you, right? Because these are excellent questions you guys are asking. Really, really, you guys have done a wonderful job. Because it is not easy or trivial or any of those things. So look what happened. Kind of flipped it upside down, right? It's not giving you exactly the same thing. It's kind of doing some like rotation or reflection or transposition going on here. So look at what happened is that row 2 became row 1 and row 1 became row 2. So yes, it must be left to right main diagonal or else the identity part doesn't hold. It'll still be commutative, I think, but you're going to lose that identity part. Yeah? You'll get a negative, but it'll be the negative version of it. So again, the identity part doesn't really hold because they're not equal to B. You'll get negative B. We feel okay there? All right. So we've established the existence of a multiplicative identity, right? Which is fantastic. Usually I have to suggest that. You guys kind of found it all on your own, which is excellent. Here's my next question. So we have a multiplicative identity. Okay, so for matrices, do we have a multiplicative inverse? What do I mean by multiplicative inverse? So what we're asking is, for any matrix A, is there some matrix B? I shouldn't say for any matrix A. For some specific matrix A, is there a matrix B such that A times B gives me the identity? So right away we should say no. But if we add on another condition, the answer becomes, well, now I'd have to think about it. What's the condition that we would need to add on to take this from being a hard no to, well, maybe? Mia? Yeah. So if we make A have to be an n by n matrix, now it becomes from a hard no to a, well, now that's an interesting question. So let's try to make this happen for a 2 by 2. Sound good? Okay. So I'm going to say, let's have the matrix, actually, let's use subscripts. That'll probably be easier to kind of see what's going on or keep things straight. So here's a matrix A that I've written as the entries A11, A12, A21, A22, and a matrix B that I've written as B11, B12, B21, B22. Everybody's okay with that? And we need that product to give us 0, 1. Everybody's good with this so far? All right. So let's go ahead and multiply these together. So when I multiply the first row of A with the first column of B, I have A11 plus or times B11. And then when I multiply row 1 by column 2, I have A11 B12 plus A12 times B22. And then we have row 2 times column 1, A12 B11 plus A22 B21. And then similarly, row 2 times column 2, so I have A21 B12 plus A22 B22. So far, so good. And this now is going to create for me a system of 4 equations. Because I know for these two matrices, each entry in my matrix must be equal to the other entry in my matrix. Is everybody okay with that notion? Basically, we're just saying this, this is equal to this, and so on and so forth. Everybody's okay with this so far, how I've gotten to this point. Okay. So, what I'm going to do, remember that my only true variables are my B's, right? Matrix B is going to be based on my choice of matrix A. A is the thing that I want to be able to take any 2 by 2 matrix and be able to find some matrix B that's going to be its inverse. So what I'm going to do here is this equation and this equation have the same B's in it, right? So that becomes a 2-variable system. And these 2 equations have the net. So that's going to become a second 2-variable system. Is everybody okay there? All right. So we'll call these 2 equations A and B. Let's say we want to eliminate the B11s in the red system. To do that, I'm going to take A21 and multiply it by equation A and add to it negative A11 times equation B to do elimination, right? So that'll give us A21, A11, B11 plus A212, B21 equals A21. And then I have negative A21, A11, B11 minus A21, A22, B2 equals 0. If I add this down, I have A21, A12, B21 minus A21, A22, B21 equals A21. Because this part just canceled out. Again, we're solving for B's, so I can notice each of these has a factor of B21. So I'm going to factor that B21 off. And then divide both sides by that quantity. And there's my one of my entries in B has to look like this. We're not going to solve the rest of these because it's far too tedious. I'm just going to tell you what they are. Everybody's okay with that? I hope so. Oops, that's not right. Negative. Wait a minute, hold on one second. Oh, yeah, that's fine. This is wrong though. And that's in the wrong order. Shoot. I know what the answer is supposed to look like. I'm just trying to make sure I have all the symbols in the right places. Did I screw something up here? Actually, you know what? It doesn't even matter. Here's the takeaway. Let's not get bogged down in all these details, right? Like you guys have already tuned out. I can see this, right? I started solving the system. There's too many letters and subscripts, and everybody's like, oh, dear God. Here's the takeaway. Is for this A inverse, that's the way we're going to write it. So that'll be the multiplicative inverse for A. We'll write it with a -1 exponent there. That doesn't mean it's 1 over A. That's just the name that we're going to give for the multiplicative inverse. Oops. A little bit here in a moment. But this would be the result that we would have gotten. There, those subscripts were probably getting hard to read, right? My apologies. Again, you guys don't have to worry. This is not the final form that we're gonna clean this up even a little bit more than this. But this is what we would have gotten from the solving the systems just a moment ago. We haven't even gotten to how we're going to actually do this. So it's going to be much, much easier than what we've done. Yeah. No. This is just bad because we're trying to get to a general statement, right? Getting to the general statement is the hard part. Using the general statement is what we'll do because we're going to do the hard thing once to find the shortcut that we'll use every time. Okay. So, is this A inverse always going to exist? Well, what could give us problems with this formula that we've written? These are fractions, right? When do we have a problem with fractions? When do we have a problem with fractions existing? When the denominator is 0, right? If a fraction has a 0 denominator, what is it? Undefined. Can we get a 0 denominator here? Yeah. So that's the first thing we have to worry about. Second, notice that each one of these has the exact same denominator, right? So I'm going to factor that out. So that it's a little less ugly looking, because all that is scalar multiplication, right? If everything is being multiplied by the same fraction, we're just talking about scalar multiplication. Oh, is it time to go?
Yeah.
Okay. We'll continue talking about this next time. Let's look here. You guys could work on homework 9, the first part of it. So the first page of homework 9 you could start, but you can't go past the first 5 questions on that because we haven't gotten to the big payoff yet in what we were just doing. So kind of, I guess, is the homework answer.
Yes, but no.
Yes. You could start some stuff, you just won't be able to finish it, which is fine, or you can wait.
Thank you.
You're welcome. We'll clean this all up next time. It'll seem less overwhelming. But it was fun. We had to explore a little bit.